Welcome back. Now in this video we're going to be looking at the reflection and transmission of light through very thin films. When I say thin films, I mean a material whose thickness is a couple factors of the wavelength of visible light. Now, like sound, light has wave-like properties, which means that if you have two beams of light and the trough of one is meeting the crest of another one, they may actually cancel out and produce no light at all. Keeping all this in mind, why don't we go ahead and take a look at the problem statement. Okay, so in this problem we have white light incident upon a thin film. The white light is composed of all wavelengths of the visible spectrum in equal proportion, and some of it will transmit through, some of it will reflect back, etc. We're told the length or the thickness of the film, and we're also told that of this white light, the wavelength of 600 nanometers undergoes fully constructive interference upon reflection. Using that information, we're supposed to find out what wavelength of reflected light undergoes destructive interference. Notice we don't have the refractive index of this thin film here. So we're going to have to find that as an intermediate step. Now the procedure here will be to use something similar to what we did in the sound videos. Recall that in the sound videos, we also had two waves of sound coming into a certain point, and we wanted to find out if they were constructively or destructively interfering. The way we solved the problem was by finding out what the difference in path that these two waves traveled. For example, if one wave traveled exactly one wavelength longer than the first wave, well, what that means is that the first wave, let's say it was at a crest, the second wave travels exactly one wavelength longer, it's also at a crest. So those line up and you have constructive interference. In other words, you get a bright spot in the sound, in terms of sound. On the other hand, if you had one wave traveling exactly half a wavelength more than the first wave, well, the first wave may have been at a crest, the second wave is now at a trough because it's a half wavelength. When you add up crested troughs, you're getting a smaller number, so you actually get a decrease in amplitude, which means that you have kind of a soft spot. All right, so the goal there was to find out what are the path length differences between the two waves. In this situation, we're going to do something very similar. But instead of dealing with path differences, we're going to deal with what's known as phase differences. Phase differences are somewhat similar to path differences. You can think of the phase as just what point in the cycle is the wave. A full cycle is 2 pi. All right, so if one wave is exactly one half cycle ahead of the other wave, that's a phase of pi. If it's exactly a full cycle ahead of the other wave, that's exactly 2 pi. If it's 2 cycles ahead, it's 4 pi, etc. So we can use phases to compare what point of the cycle they are. And we can see that if we just set that equal to pi or 3 pi or 5 pi, well, now you're lining up crests and troughs. You can have destructive interference. Whereas if you have multiples of 2 pi, 4 pi, 6 pi, you're lining up crests and crests. So you have constructive interference. So what the difference in phase is will tell us what kind of interference it is. Now the goal is to find the phase difference. So how do we find phase differences? Phase differences arise in two manners when you're dealing with light upon boundaries like this. The first way is by a path length difference. This is something very similar to what we did in the sound chapter. So it's going to be some 2 pi times whatever the fraction of the extra distance the other wave traveled, which I'll write as this. Okay. And just to remind you, lambda n is the wavelength inside the particular material, which is going to be less than its vacuum wavelength. It always decreases by the refractive index. Now, let's just give you a few examples for this. So let's say that you have one wave traveling exactly one wavelength longer than the other wave. All right? In that case, your delta D is one wavelength because the difference in distances they traveled is one wavelength. Delta D divided by the wavelength will be one wavelength divided by a wavelength is just one. So you get a phase difference of 2 pi. That makes sense. It's traveled one wavelength longer, so it's back to a full cycle. It's traveled one extra cycle. And we know that one cycle is 2 pi. On the other hand, if you have one wave traveling half a wavelength more, well, this will just give you half, so you get a phase of pi. And as I mentioned, half a cycle is equal to a phase of pi. Okay? So this is how you convert path length differences to phase differences, but we're going to only be dealing with phase differences here. We can find this by looking at the situation and then just converting it to the delta phi. Now, the reason we're actually using phase differences as opposed to path differences is because the second reason, you get a phase difference upon reflection. And you can't express this phase difference as any kind of path. So that's why we use phases here. And this one occurs when you have reflection but it only occurs when you're reflecting off a boundary, in which case the incident light is coming from a lower index towards a higher index. For example, along this first boundary here, this is an index of 1 because it's air, and then this is an index of something higher than air, so something higher than 1. So you're going to have some white light coming here, and some of it will reflect. Because it's going from a low index to a high index, that reflection will automatically undergo a phase of 180 degrees or pi radians. So whatever light is coming in at this point, let's say it's right at its crest, right as it's about to hit that boundary, it's at its crest, the reflected light will automatically be at its trough at that moment. Okay? So that's always going to occur from a low to a high index. It's always going to automatically just pick up a phase of pi. All right, so now let's apply this to the situation we have in our given problem. Let me just redraw this a little clearer. And let me just talk about the two waves that we're going to compare. All right, so we have all the white light coming in. Some of it reflects off the first boundary. And I'm drawing that at an angle even though it's not really coming out at an angle, just to visualize it better. And then some of it reflects, well, some of it goes through and then reflects off the back boundary and comes back. Notice that, I'm going to call the first one 1 and the second one 2. Notice that wave 1 only traveled this distance by that point, whereas wave 2 had to travel this extra distance by that point. Also, they undergo different reflections. So you're going to have all kinds of phase differences arising from the difference in these paths. Now, what we need to do is tabulate what these phase differences are, which I will do right below it. So the goal here is to find delta phi. And basically what we want to do is compare what the phases are right after they reflect. Okay? The first one right after it reflects is going to be right here. The second one right after it reflects, well, it's going to have to go all the way this distance and then come back there. So we're going to compare where these two waves are right about this point after they reflected, in which case the first one reflected, but the second one had to travel a little extra plus reflecting. Phi 1, the phase it picks up, well, the light comes in, and then it just reflects off this boundary, but doesn't really go any extra distance because we're looking at that point. Does it pick up a phase from reflection? Yeah, it does, because it goes from a low index to a high index. So it automatically picks up a phase of pi. Okay. Now the second one, let's see what happens to that one. That one's going to go through. So at this point it's transmitting through, no phase change. But it's going to travel this extra distance from here to here. Okay. So that extra distance is going to give a phase based on this formula. So you're going to have 2 pi times, what is the distance it traveled? Well, the distance it traveled is the thickness of the film, or L. Okay, by that time we're at the back boundary. Then it's going to reflect. It won't pick up a phase of pi, though, because it's reflecting from a high index to a low index. So no phase change upon reflection. And then it's going to travel back in this distance, which will again pick up a phase of 2 pi times L over lambda n. Okay. Now what we want is the phase difference to be, well, we want it to be constructive for lambda is 600 nanometers. Okay, so let me write over here, let me go ahead and write lambda 600. This is for this particular case. We want the interference to be constructive, which means the phase difference has to be some multiple of 2 pi. Remember, 2 pi is one cycle. We want it to get back to its original point in the cycle, so that crests line up with crest and you get constructive interference. So we want this to be some multiple of 2 pi. We don't know what that multiple is. We just know it's an integer. Okay. Now what you can do here is plug in these guys for phi 2 and phi 1, and since you know the lambda, and you know L, you can actually solve for n, the refractive index, in terms of this integer m. Now you don't know the integer m, but you can try a few integers, and you'll see that only some of the integers really make sense, and they give you a refractive index that's physical. So go ahead and do that now, and try to find a reasonable refractive index, and we'll come back and finish up the problem. All right, you should find that the refractive index has this particular form. Over 4L. Okay, and like I said, we don't know m. We don't know the integer m. But let's go ahead and plug in a few values of m. And we'll see what n is. And really only one of them kind of makes sense. So when m is 0, you get a refractive index of 0.55. Can't be less than error, so that doesn't work. When m is 1, you get 1.65. And then when n is 2, you get 2.75. Now, 2.75 is quite high. It's actually bigger than the refractive index of diamond, which has a very high refractive index. So this is the only reasonable number, so we're going to say that the refractive index of this material must be around 1.65. Now, given that, we got to solve the second part of the problem, or the actual question it's asking, which is, what is the wavelength of reflected light that is destructively interfering? So the process will be similar here. You really just want to do the exact same thing we did here, but now we want delta phi to equal some odd multiple of pi. So you can write that as this. You can write it as 2m plus 1 times pi, where m is an integer. If you plug in a few integers here, you'll see that it just gives you like 1, 3, and 5. And then do the same thing we did a moment ago. We already know the phase differences because we're looking at the same beams of light. So go ahead and use these guys, plug them in, and find out what the lambda is. Now that we know n, we're looking for lambda. So find out what the lambda is such that this equation is satisfied, and look for the lambda that's in the visible spectrum, and that'll give us what we're looking for. So go ahead and finish that up, and we'll just finish with the problem then. All right, so combining these two formulas with this formula, you should find the following expression for the reflected wavelengths. 2ln over m. Again, m is an integer, so we got to plug in some integers to see what we get here. When you plug in 1, you get 900 nanometers. When you plug in 2, you get 450. And that's in the visible spectrum, so that's what we're looking for. So that's the wavelength that you will not really be very present in the reflected beam because it's destructively interfering. All right? So that's the wavelength we're looking for in the problem. And let me just say a few words about the way I approach this problem. This method is not the way it's done in a lot of books. They just give you a bunch of formulas and say, well, this formula applies when you have a low index to a high index and you're looking for a reflection, or this formula applies when you have a high index to a low index and you're looking for transmission or something. But those formulas, first of all, they belie the physics. They don't really tell you where they came from. They may derive them, but once you start using them, you forget where they came from. So they kind of hide the physics and what's physically happening here. Whereas these formulas, it just tells you basically how to do it systematically. No matter what the situation is, all you have to know how to do is find phase differences. And the phase differences arise only from paths, differences in path lengths, or from reflections. So if you can look at the situation, no matter what the situation is, and follow these waves piece by piece, adding up all the phase differences, and then all you have to do is either set them equal to this for constructive interference or equal to this formula for destructive interference. Then you can solve for any situation, regardless of how many times his beam is reflecting, etc. So it's a much more versatile way of solving these problems, and it makes the physics a little more transparent. Keeping that in mind, let me go ahead and just give you one last question to think about. The answer is going to be written up in the solution. I won't cover it in the video. And the question is, what color is the transmitted light? What that means basically is which of these wavelengths will constructively interfere in the beams that come through here. All right? So basically you have some of the light will go straight through, some of it will go through, reflect, and then go through like that. So you want to compare those two beams. Doing the same method we did here, find out which wavelengths constructively interfere. And that one will be the most present in the light, and the light will assume that color by our eyes. Try that out. The answer is written up in the solution, and I'll stop there, take a look at the summary. We'll see you next time.